Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my pleasure this morning to introduce Glenn Judd. Glenn's coming to us from Carnegie Mellon University, where he's Peter Sikin's a student. He's a candidate for the networking research group, and he'll be talking to us today about some of his thesis work, which is an emulation system for better understanding and experimenting with wireless networks. Take it away, Glenn.
Thank you. All right, so the motivation behind this work is, of course, that wireless networks are everywhere these days, whether it's in a campus environment like we have here or in people's homes, or also in so-called hotspots where people, due to the ease of installing and using the LAN, they can draw in more customers by offering internet service there. And so there are also some emerging applications such as mesh networks and home entertainment networks, replacing the rat's nest behind everybody's TV with a wireless network, and also intervehicular networks, which I'll talk a little bit more about later. And as researchers, I think the way that we can help is, of course, to understand better what is going on in these networks, and then to improve them in the cases where they fail. And also we can leverage the capabilities provided by these networks to provide end users with new and interesting functionality. One example would be a contextual aware application which is based then on the localization implicitly provided by wireless networks. One challenge we face, though, as wireless researchers is conducting wireless experiments. Wireless experiments are fundamentally difficult. And this is unlike a wired network where we can just abstract away the physical layer. In wired networks, the physical layer fundamentally affects the higher layers. So something like, say, TCP segment size has a very physical layer impact on, say, something like spatial reuse. And so as researchers, we have a trade-off between the control and the repeatability, between control and repeatability, that is. And ideally, we'd have it all. We'd be able to run real applications in a real network, and we'd have a real OS, but we'd be able to control the experiment so that external factors, we wouldn't have some unknown variable in our experiment that we had to just sort of wave our hands at. So if we think about that for a minute, we think about how we might, one way that we can naturally gain realism is to use a test bed. So let's say we had a building somewhere on this campus that we wanted to conduct experiments at. Maybe we would want to look at, say, wireless routing in a mesh. And one day we run an experiment and get result set A, and on the next day we run an experiment and get result set B. And we might conclude that, the change in our algorithm that we did between those 2 days resulted in some improvement that we saw. In a wireless network, though, in reality what might have happened, there could have been just a large truck parked outside the building on day A that was maybe bouncing the signals back in and changing the performance of our network. So this is the kind of nasty effect that we just assume not have, but that we fundamentally get when we use a wireless testbed. Also, wireless testbeds are more cumbersome than we'd like. So if we consider the intervehicular networking example that I discussed about earlier, I'll explain that microwave in a second, an intervehicular networking experiment in a testbed fundamentally requires getting in the cars and driving, which is very cumbersome and is annoying. So researchers have actually resorted to a few techniques. One, to control repeatability, they've used that microwave I've shown there. Some researchers have stuck the laptops inside the microwave and opened and shut the door to give themselves a repeatable test bed, if you will. So we'd rather not have that. What most people have done, instead of resorting to that sort of measure, is they've gone to simulation. And simulation overcomes these problems that I've talked about. We no longer have to worry about that truck parked outside the building. If it's parked outside our simulator, who cares? Also, our simulator sits on our desktop, which is great. We don't have to get in the car. We don't have to drive. And if we wanted to compare our results with other researchers, we can easily do that. The results on the simulator should be the same whether we're here in Seattle area or whether we're in Europe. So simulators are quite nice, but there's a new issue, and that is a lack of realism. When we use a simulator, we are not using the real hardware, and we have to make assumptions about the way it works. And it's difficult to keep up with the rapid changing pace of hardware. At 802.11, I don't even know what the latest letter is right now. Also, applications are generally not directly supported on simulators. So if we want to run an application in a simulator and then run it in a test bed, we usually have to port the application between the two. And so what people typically do is either conduct a test bed-based evaluation of their various wireless networks, or they conduct a pure simulation approach. There isn't too much crossover between the two because that generally entails duplicate effort. And there is a temptation, I believe, to let simulation then become sort of the gold standard by which our experiments are measured. And this is undesirable because at some point in a wireless network you really need to get out into the real world and encounter the various impairments on the wireless channel that exist in the real world, and encounter also the behavior of the real devices. And if researchers aren't getting any benefit for doing that, if simulation becomes sort of the gold standard, if it works in the simulator, it's considered good to go, then there's no reward for going out there to the real world. So on the one hand, we have test beds that provide us with realism. And on the other hand, we have simulators that give us the control and the repeatability that we want when we conduct experiments. So one way to strike a compromise between the two is to use emulation. That is, to use real components and execution in real time. So doing this, we can run real applications, and we have a real OS. And most emulators to date, however, have used a very simplified Mac and physical layer. They have the problem that they have addressed is the running of real applications. And then they've done something simple like drop packets to try and make it look like a wireless network. The contribution of the work I'm discussing today is a physical layer wireless simulator. That is, one that lets us go all the way down to the physical layer, use a real wireless device and real wireless devices, and to be able to make them, to be able to control them as if they were running in a traditional packet simulator. And this has appeared in, so the main portion of my talk that I'm going to be covering has appeared in NSDI and HotNet. So I'm going to be mostly covering what's been, what we presented previously there, but with some addition of some new material. So to give an outline of where I'm headed, first I'm going to be talking about this emulation approach that I've developed for improving wireless experimentation. And then I'm next going to present some of our early results that we've gathered using this approach. And then I'll talk about related work, some additional research I've done at CMU, and then I'll discuss briefly some future research directions and conclude. So if we consider the testbed approach for a second, in a testbed we have nodes that are distributed in a signal propagation environment. And so there were a couple of problems. First of all, there was the issue that the testbed is cumbersome. So if we consider that vehicular networking example, you had to get in the vehicles and drive, which was undesirable. And also, we had, even in a fixed testbed, things can come in and out of the network that are outside of our control. And anything moving inside of that signal propagation environment affects the behavior of that network. Introduces a variable into our experiments that we just as soon not have there. And moreover, that motion will never occur the same way twice. And so we can never exactly repeat that experiment in a real testbed. So what we'd like is so the key idea of the approach I've taken is to virtualize that signal propagation environment. Conceptually, what I've done is rip the antennas off of the wireless devices and then hook them up via coaxial cable to a virtualized signal propagation environment. And so once we do this, the devices don't talk over the air. There's no more communication over the air in this approach that I'm going to talk about here. All right, so this approach then gives us realism in that we have the real wireless devices doing what they do out there in the wireless world, and we have their full capabilities, of course, and we can naturally run the real operating system and the real applications. And this gives us an accurate approach without coupling us to a particular physical locale like one would get in, say, a test bed. And this complements those two approaches that I've discussed in that with a wireless test bed we can run the same experiments in this emulation approach that we could run in the test bed, and we could do, say, the first 80% of our experiments inside this emulation approach. Then we could go out for the remaining 20% and conduct some experiments to verify the results that we saw, and so on, in a real test bed. And this approach complements simulation in that this approach can be used to develop better simulators. We can characterize devices and their interaction very, very accurately. All right, so this figure shows the architecture of this wireless emulator that I've developed. Again, we have wireless devices, which are depicted as laptops here, but they can be anything. They're connected via coaxial cable into a magic box here. That's shown here as a signal propagation environment. And the operation of the end devices and the signal propagation emulation is controlled by the computer shown on the top. That's called the emulation control node. And it runs scripts that controls the running of applications on those nodes, on the end nodes, and coordinates that with the emulation of the signal propagation environment.
For what kinds of wireless devices is coaxial cable a problem?
A problem?
Yeah, like is there some frequency range in which it is no longer a good medium for getting things to the signal propagation environment?
I'm not aware of it. Certainly the higher you get in gigahertz, the more attenuation you get in the coaxial cable, but I'm not aware of any of that where it completely flakes out. Certainly if you can fab a device that's going to work at all, it can probably have some coax cable that it can work with. These coax cables are very short, I should say. Okay, maybe it'll be a little clearer once I show this next diagram. So if I dig into that magic box a little further, it breaks out as follows. Co-located with each wireless device, we have a signal conversion module. And that is what attaches via coax cable to the wireless device. So it's a very short run of coaxial cable. And then, so the job then of that signal conversion module is when each wireless device transmits, that module converts the signal that's being transmitted to digital form. And then the longer run out to the central FPGA-based DSP engine there, that's done digitally. So once the signals are sent to that DSP engine digitally then, the job of that engine is to impair the signals as if they were floating around in the wireless ether. So for instance, the signals can be attenuated and they can be split to emulate reflections, etc. And so on receive, what we do for each receiver is we sum the signals that are destined for that receiver and send them back out to that receiver's signal conversion module, where they are converted from digital back into analog and sent out to the device so that the device does what it normally does. And we don't have to worry about how that device behaves because it's the real device. All right. So it's worth asking why this is better than simulation, because at some point we are performing a simulation. But our simulation is working at a much finer grained of detail than a traditional packet-driven simulator, like say NS2 OpNet or QualNet is. So if we consider the process of packet transmission and reception, in our emulated case, we have an actual modulated.
So this is actually a question about your previous slide, but it took me a while to formulate it. But you don't have to go back. I think it's just. Does this handle MIMO antennas?
That's an excellent question. Let me get back. The short answer is yes. Remind me at the end to get back to that. MIMO is challenging. The short answer is yes. Remind me at the end to be sure to get back to that.
Okay, so the question I've got is, so are you actually digitally sampling the 2.4 gigahertz signal then?
We down convert first, then digitally sample.
Okay.
So I'll show that architecture a little bit more in a second.
How much delay gets involved or introduced in this? And does that, I mean, it seems like a lot of what Macs do is try to avoid hidden terminal problems and back off to avoid talking over each other, that kind of thing. If you add delay in there, it seems like it'll affect all those sort of algorithms.
That's a very good question. The delays we're talking about are in the order of nanoseconds here. So in general, the Mac protocols are much higher. So there is essentially this approach adds there is an artificial delay added by the emulator that you can never go below. So effectively, you can never get the effect would be as if in the real world you could never get closer than a certain distance in terms of delay. But we're on the order of nanoseconds, and most Mac protocols really operate in the order of microseconds. So it really shouldn't affect the Mac per se. But if you were to be looking at that level of detail, that would be an issue to consider.
So you have time synchronization in between all of your sampling nodes, so that there's this concept of order between the various events and the various devices?
We don't. Basically, we stream the signals between them, so I don't need to explicitly synchronize the events per se. There's a real OS out there, so I'm not controlling down. The OS has some amount of non-determinism in there, You know what I mean? So I'm not getting rid of that. That is there. So that makes sense.
But is there an ordering of when things hit the proverbial air, that you know that there'll be a collision between packet A and packet B?
I don't have to decide about the collisions. That happens naturally. All I control is the signal propagation modeling between them.
In other words, you're sampling everything in one place. All these coaxial cables go into a single computer with one time base.
A giant FPGA.
Okay. Yes. So time. Yes.
Okay. So maybe getting quickly back to the example of packet transmission and reception in an emulator versus that in a simulator. In the emulator, we have a real waveform. In a simulator, you have some abstract region of signal strength. And so if then we had say we had a couple interfering sources and a noise, which might be due to the device itself or maybe thermal radiation. In the emulator, we have the real interfering signals and the real noise present on the device, and we could inject a little noise to emulate the thermal radiation. In the simulator, again, you just have abstract regions of signal strength. So when we want to decide whether a packet is received, what we do is we just sum these signals together, send them out to the card, and let the card decide. So the card does, it performs real reception. So if it has say a rake receiver or maybe a good equalizer on the card, it could that could potentially help the reception. Whereas in a simulator, we just typically look things up in a theoretical bit error rate table, or we sum up the signals to get regions of signal to interference and noise ratio, look that up in a bit error rate table, and then decide receive, not received. So a couple important properties of this emulator is it's technology agnostic, and again, the device behavior is not simulated at all, it's real.
Have you or somebody else gone and quantified or come up with qualitative, quantitative examples where the difference between these two approaches is significant?
I have some very low-level behavior that I'm going to be getting to in the next slides, and I don't think you'll see that in any simulator. So I should say, on the link level, it is possible to run a non-real-time simulation that can be very realistic in device behavior, something like MATLAB Simulink. You can perform some very realistic analysis. Typically, these packet-level simulators that have, say, a full protocol stack attached to them have not gone down to that level of detail because it would just be computationally intractable. So we can run it. So I'm not saying you can't necessarily do this. I think it's generally infeasible to have a full protocol stack attached to a very realistic radio simulator as well. Does that make sense?
I guess I was asking a slightly different question. Can you take your approach, to take the simulator approach, and show how under
sort of beat up on the simulator and say bad, bad, bad?
Well, no.
Yes. That's what I wanted to see.
Yeah, see how they come up with different answers.
Yeah, I've done a little of it. I haven't done much. Some of the results I get later on, you can't get it with the simulator. And maybe I should. There have been some other people that have compared simulators to the real world and said bad, bad, bad. I could do some of that. Yeah, that's kind of on my to-do list. Okay, so I've talked about the architecture. So I'm going to go on to the implementation. Any more questions before I discuss the implementation? Okay. So if we look at the architecture picture again, what I've done then for each of those components, we've created custom hardware to implement the functionality. So the central board there is really a giant FPGA with ports to connect out to these signal conversion modules. Now if I zoom in on that signal conversion module, we see that it's split up into several different boards, and I'll walk through the process. So the wireless device in this case is shown as the laptop. And again, that connects to this board via a very short cable. And when we transmit, the signal first enters an RF front end. And that is what converts the signal down from the microwave range down into a range that can be digitized effectively. And and the A to D converter shown there on the right, analog to digital converter shown on the right, is what performs that digitizing. And it is capable of digitizing about 100 megahertz. And the A to D technology is the limiter, really, on how much we can grab in a single swath.
Down convert to what frequency?
We down convert to, well...
What's your IF?
So to get really technical, we're undersampling. So we have a high IF of about, right now our clock actually runs, in the actual system that's running right now, it runs at, we run at 160 megahertz. And we down convert to just above that so that we can undersample. Undersampling gives us some advantages I can talk about offline. So then Once we enter the A to D, the analog to digital converter, that is sent to this board labeled DSC, that stands for digital signal conversion. That board really just plumbs all the digital logic between the analog to digital converter, the digital analog converter, and that middle board. It just plumbs them all together. But because we have an FPGA there, we can offload some of that processing from the middle board into these daughter cards in certain situations. So on reception, the opposite occurs. The computed signal comes back from that DSP engine into the DSC card. It's sent to the digital analog converter, up-converted, which sends it to the RF front end, which up-converts it to microwave, and it goes back out to the device. And there are some tricky points, which I'm not going to cover in this talk, about designing that RF front end in order to support half-duplex nodes and also to avoid crosstalk between the different signal conversion modules, which I can talk about offline if people are interested. All right, so with the power of emulating signal propagation comes the challenge of doing it in a good manner. I emphasize again that the device behavior is real, so I don't make any assumptions about interference range, reception range that you typically read in a simulation-based paper. All of that is real. The device just does what it does. So there are three different approaches that we have used or three different categories of approaches that can be used. We've used two of these so far in emulating signal propagation. The first is modeling. And this is typically broken into two parts, large-scale path loss and small-scale fading. Go ahead.
Back to the point, you don't assume an interference range, but all of your experiment is being conducted in a room. So how do you emulate something that's bigger than a room? You have to assume something about how the power attenuates from one node to another.
Sure. So we control, so they don't talk over the air. So I should say, consider these laptops or devices to be in Faraday cages, so they don't talk over the air. They're only through our device. So through our device, we completely control the signal. So you can view us as sort of, we can play God, if you will, with these signals to some degree.
But you have to decide how the power attenuates if you want to emulate longer distances. Right?
So we do decide how the power attenuates. That's correct.
So, I mean, you are, in some sense, making assumptions about reception range and interference ranges.
No, we're assuming the path loss. Yeah. But whether the device can extract out the interference or...
Right, but so... Hold on. So imagine you had a bit-level simulator entirely done in software where you go all the way down to the point, you get to the point where the device tries to talk to the channel, and instead of actually encoding it as RF, you feed it to a big simulator that decides how these bits are going to attenuate over distance, and how they're going to combine and interfere with each other, and then it gets fed back out to the software. So we're not doing any RF stuff at all. It sounds like your argument is that makes too many assumptions about things like what the interference range is, what the reception range is, and so you'd rather do it in the real RF domain rather than the software domain. But it sounds like you're really making the same set of assumptions as that hypothetical software-only simulator. It's just that you're implementing your assumptions in the RF domain instead of the software domain.
No, I totally disagree. The key difference is that you've got the entire stack and the entire electronics of the existing device. All of its microcode, all of its features and special warts are all there. And so you don't have to rewrite the simulator when you get a new microcode release from Linksys. And so everything that's in Linksys or D-Link or whatever is all there. The only thing he's manipulating is the RF path in-game.
It's more than that. There is really no such thing as a reception range or an interference range. Simply what it means is that if I get a signal at this signal-to-noise ratio, can I decode it? Okay, that's all that matters. So all he's doing is that he's getting the signal from where it was sent.
That's not the receiver, but between the sender and the receiver, you have to plug in something.
So what does reception range mean? If there is a thick, slab of concrete in between, then your reception range is whatever, 1 pulse. I mean, it completely depends on what path loss model you assume.
These are the ones here.
Exactly. That's the second. This is the second bullet.
Okay, let's try table it for.
the slide and then we'll
All right, I tell you, I'm saying.
Okay. So we'll hit the question section and we can dig into this because probably some people will want to leave before that, I'm guessing. Okay, so getting back to the modeling. So what I do need to do is I do need a model, which can be very challenging. Well, I should say I do need to emulate, and one way we do that is to use some existing models. Large-scale path loss, again, is the average signal strength over time. So if we consider a receiver that's moving away from a transmitter, large-scale path loss would be, one example would be it decreases in an inverse R-squared fashion. Then on top of that, we put on top of that small scale fading, and that is relative. That depends on the velocity of things in the environment or the transmitter and receiver themselves. So this is, and there are some accepted statistical models in the community for these that we currently have implemented right now.
Actually, the question I wanted to ask is something opposite of what you just said, which is if you go out and using your setup, try to validate these statistical models.
So I'm not. No, I have not. And certainly, in some sense, I'm sure you can find an environment where they fail. They're idealized. You have uniformly distributed scatters, and so on and so on and so on. So I haven't done that. But the next approach maybe gets at that, and that is what we can do is we can actually record an environment. So we can take, for instance, one way we can do that is with RSSI. So we can move the receiver again, and we can send little packets from the transmitter to the receiver and record the signal strength that was present at the receiver. So we can, in some sense, capture the real environment and then replay it in the emulator again and again and again. When we do that, though, we don't need to worry about the truck. If the truck was there that day when we captured it, great. It'll always be there in our experiments. All right. And another thing you can do is you can use a channel sounder to get a very fine-grained detail recording the channel. So the RSSI doesn't include full multipath information. A channel sounder can capture that if you have that. And if you have one of those devices, we could use it in the emulator. I haven't done that. The other approach that... Go ahead. It basically records the signal strength. It records the full path information between the transmitter and the receiver. That's what you can think of. So it'll tell you, oh, you have 7 reflections or whatever.
It's the $100,000 piece of equipment. We do actually have one of these in the building, and basically does a frequency sweep of the range and some chirping patterns, and based on that, you can sort of pull out, what is. If you think about the signal processing, what is the H function as a what's the channel transfer function of that space between the sounding antenna and the receiving antenna? You can move the receiving antenna around, and then it totally characterizes them.
So that would kind of be an idealized approach, although they're a little cumbersome. You can't have 20 of them and drive them in cars like you can with the RSSI approach. It's easy to do. Lots of devices. Another approach you could use that we have not done is ray tracing. We could do what the graphics guys do. Send out rays and then compute the received signal strength. Again, we haven't done this, but it could be done. Another approach that could be taken.
I have a question there. I remember from when I was studying graphics that even ray tracing even the ray tracing that was implemented in graphics hardware at first wasn't real time when I was studying it. Second, they made assumption that they tended to cut corners in ways that were fine because all they were trying to do was present nice pictures, right? So that if it looked good to a human eye, it was great. And do we have any, I actually don't remember what those corners that they cut were, but are they the same corners that you would want to cut here? Or
you have this, so I'm not a graphics guy either, but I can answer. Basically, I view these as being from least accurate to most accurate, the least accurate being just the model approach. You don't consider the environment, just large-scale path loss, statistical fading. The next step above that is a ray trace. So that would be, hey, we're cutting corners, but still we've got some multipath information that we don't have in the other approach. And it looks, you look at Toy Story, it looks similar to a real house if you got down to that level. So you could get something that looks pretty good from an RF standpoint, but wouldn't be perfect. And then the next approach would be go out in the real world and record, and ideally with the channel sounders. That's how you're going to get as close to reality as possible. There's always going to be some error anytime you measure something, of course. Okay, so maybe to show quickly how this program works inside this. To show how we implement channel models inside of the FPGA. So this is a diagram showing if we could blow up that FPGA and look at the circuit that's running it, look at the program that's running it. What we do is we take, for every input signal that comes in, we send it into a delay pipe, is what I like to call it, or a tap delay line if you're an engineer. So inside this delay pipe, we just repeatedly copy the signal so that at stages further and further into the pipe, we have older and older copies of the signal. Then what we can do is at a specified delay, we can pull off a copy of the signal and scale it by whatever factor we want. So we do this for every single source. And then for each receiver, we decide which delay it wants to hear from each source, and we just sum them up and send them out to the receiver. So it's a fairly simple circuit. We do that for every single source and receiver set. And then the real trick really is the modeling. That is changing those scaling factors and picking the delays appropriately in order to model our environment.
How many sources and receivers can you support?
Very good question. So the limitation, as it turns out in the hardware, is on the multipliers inside the FPGA. That tends to be the most. So it's an FPGA, so we don't have to fix. We can trade things off. So if we wanted a really long delay pipe, then maybe our limiting resource would be logic on the FPGA. For lots of sources, the resource quickly turns out to be the multipliers on the FPGA, since you have order n squared possible interactions. So if you want to support the full n squared, our current FPGA that we're using supports a total of 15. Yeah, 15 sources and things. So scale is definitely one of the biggest challenges with this approach that I'm talking about. All right, so now I'd like to give a demo. So the example scenario here is the intervehicular communication scenario that I've alluded to a few times. That is, all major automobile manufacturers are looking at putting wireless networks into their into automobiles. I'm not sure if they have some safety applications, and I'm sure they're going to try and sell you something as well. But how they conduct experiments is challenging for them, because they need to get in the cars and drive around, or they result in simulation, which is, again, not as realistic as we would like. So this approach, the emulator, represents, again, a middle ground where we can get the real devices, the real hardware stack, running on them in a very realistic environment. And all right, so now I'd like to take you out to. So right now in Pittsburgh we have the emulator fired up with 4 laptops attached to it. So if the internet cooperates with me here, I can. Okay, so this is that EMU control node that I talked about before, running in Pittsburgh right now. And what's going to come up next is going to be a visualizer of the physical environment that's being emulated. In this case, we're emulating an environment somewhere around here. So the signal propagation modeling, in this case, it's all modeled. So it doesn't necessarily correspond to what we've got going on here, but we could go out and record it. So what we're going to have now is we're going to have some vehicles or some emulated vehicles that are going to show up, and they're going to start driving around a loop on this in this environment. And then the rear node in this convoy here is going to be blasting out UDP broadcasts, and the other nodes are going to be recording how many packets they hear. So first of all, the path loss graph shown on the right there shows shows the path loss that we're emulating between the rear node and the front node. And you can see that the large-scale path loss depends on distance. As they approach a corner, they'll get closer, and the average will increase. And then you'll notice that because they're moving, we have fading going on, that rapid, in this case it's Ricean fading. And then on the top, you see the results of this UDP throughput experiment. That is, the colors correspond to the nodes, so the number of packets received by the closest node to the rear guy, MU3, is shown in green, and as you can see, it receives, as you'd expect, the most packets. And then the least packets are being received by the guy in the front of the convoy. And again, this packet reception there are actually, right now in Pittsburgh, real packets being sent through the emulator right now. And I'm not deciding how many are making it through at all. All I do is send out to the emulator this path loss, and then the devices decide how many packets exactly make it through. Is there any questions about what's going on here?
So this is 82.11b.
That's right. This is all 82.11b.
Can you support G at high data rates at 54?
Sure, we can. Yeah. So the answer is yes. The biggest question for us is the frequency band, and we can support. It's in the same band, so sure. A, we would need to make a new RF front end. You swap out that RF front end, and we can do it. Although we might need to, A has such a large bandwidth, we might need to change something to get that whole bandwidth.
So you recorded the path loss model earlier by driving around using RSS sampling?
I have done that. I didn't do that here.
Oh, okay.
No, this is strictly model.
Oh, this is strictly.
It would have been really cool if I had recorded it, but I didn't have to.
And this is a picture of like the building 33 at the bottom.
Yeah, it was like some conference center.
Yeah, that's the Microsoft Conference Center.
Okay.
So this is a deterministic simulation, which means if I run it again tomorrow, I'll get the exact same number?
The signal propagation is deterministic. Because I have a real OS and real devices, there can be some sort of non-determinism in that by the nature of an OS.
How often does the channel model get updated?
Very good question. We can very often is I guess the answer. Certainly much less than the channel coherence. Channel coherence time on a network like this you'd expect to be maybe a millisecond or so. So I'm updating much more frequently than that. What is the number? We have a, so right now there's a question of where you actually compute the fading parameters. Right now we're doing it all out on that PC. And so we're using an Ethernet connection to send out the scaling factors to the emulator. So that's the sort of our bottleneck. Our future implementations are going to push that computation into the FPGA itself so that that's not as much of a bottleneck.
Oh, but the PC still has to, presumably the PC knows where the emulated things are.
Yeah,
It's computing the fading and then from there computing the scaling factors and pushing that out. So
that's what's going on now. In the future, we don't want it to be, we want it to just tell the FPGA where things are and let it compute the factors. To
push the whole model environment into FPGA?
Push part of the, not the, push the signal propagation modeling into the fading in particular. Out.
To go from distance to fading requires an environment model, which presumably is, in other words, out in the desert is going to be different than inside of a building.
Sure.
So it seems like right now that knowledge is building into the PC, but you're talking about moving that into the FPGA.
Some of that. Oh, in particular, we were talking about moving the Rising and Rayleigh fading models into the PC. If you're recording, that'll probably need to stay out into the FPGA. The recorded would probably need to stay out. There is a bottleneck there between how often we can. For 4 nodes, it's basically no issue. When we got to the full 15 and you have over 200 of these channels that you need to update, then maybe I think we'd still be under the microsecond, I believe, if I remember this calculation correctly. But we want to push some of that down in there as much as possible to offload the PC. Okay. So the nice things about this again are that we can run that every time they're going around this loop, the signal propagation is going to be the same, and so we can change our routing algorithm and not worry that the signal propagation environment changed. And we could, if I'd had more time and there had been 4 of me or something, I could have gone and recorded this this channel and then replayed it in here. All right. So I'll leave that running in Pittsburgh and then come back here too. Okay, so now I'm going to switch gears and talk about some of the results I've gathered using the simulator so far. Now, all of these results that I'm going to be talking about are going to be quite low level, but I don't want you to throw that. I want the real aim of this is higher level experiments like I just showed in the demo. So again, these are going to be very low level experiments because basically we spent most of our time developing the simulator. Now I'm moving up the protocol stack, if you will, starting at link level effects and then looking up. So the first result I'd like to talk about has to do with the problem of localization using signal strength. There are 2 general methods one could use to localize devices in a wireless network. One is to use multilateration, that is, or more colloquial known as triangulation. So if we consider a building where we have 3 access points shown as circles here that we want to, and a device shown as a star that we want to locate, what we do using multilateration is record the signal strength from the devices and then turn that signal strength using some path loss model into a distance, and then we can locate where the device is. Now this requires, of course, knowledge of where the access points are, their power, and the real challenge here is the model of the path loss. But on the device side, what it requires is linear RSSI measurements. And the so-called fingerprinting technique takes a different approach. That is, before we ever want to measure where a device is, we go throughout the building and we sample the signal strength from all access points at different in a grid fashion. And then what we do is when we want to locate our device shown as a star, we again measure the signal strengths and compare it to our database and simply pick the closest point in the database. All right. This requires single measurements, of course, beforehand. But on the device side, what it requires is consistent measurements across different devices if it's to be fully accurate. And so I just want to look really quickly at these device-specific behaviors. That is, how accurate the RSSI is. And in particular, whether it's linear and consistent. So to do this, we use the emulator to hook up a transmitter and some receivers. And we sent packets and had the receivers measure the RSSI. And then we saw how accurate they are. So we sent packets between -70, which is very strong, and -100, which is very weak. dBm from the transmitter to the receiver. And we sent 500 packets an average of the signal strength for each of these in 1 dB increments. And then we did this for 2 different models of cards and for several different actual cards. So what we'd expect to see then, if we plot the received signal strength on an x-axis and the actual received signal strength on the x-axis and what the card thought it was, the RSSI received signal strength indicated on the y-axis, we expect to get a nice line that as we step down 1 dB in actual received signal strength, we should see the same thing in RSSI. And then if we repeat this test across multiple cards, it should fall right on top of itself. And so what we got in reality is shown here for the prism cards. An idealized result is shown with the gold line. That shows a slope of 1 dB like we'd like. So we see at the start, and for higher RSS values, we see that we are pretty linear. That looks pretty good. As we get down to the lower the weaker received signal strengths, we see that we lose linearity down there. The more dominant effect, of course, that we see is that across the the x-axis here again is the received signal strength, the y-axis is what the card thought it was, and the different series are the results for different cards. So the dominant effect that we see here is that there is a pretty big variation in what the cards believed the received signal strength was. And so,
your calculation is correct. In the sense, were you in a screen room where there was no other possibilities of interference or multicasting?
This is all in the emulator. So, yeah, this is all done with the emulator. Sorry. So the whole point of this was the emulator let us do this in a very controlled, repeatable fashion.
I guess this may be the same question, but how do you know how repeatable the emulator actually is? In other words, this could be, for example, that you did it with 5 different copies of your RF front end and variation there.
In this case, I used the same one. This is a calibration question, essentially. How good can we calibrate the emulator?
Well, I mean, you're asking how well can you calibrate these cards, and unless you can separate out the calibration of your system with the calibration of the cards, then you don't know what the result is actually telling you.
So in this case, I tightly controlled that by using the same RF front ends, the same path to try and. So in this case, the absolute value has on the x-axis has here an error bar, which isn't shown of maybe about a dB, but the variation then should be less than that. So certainly less than the 10 dB that we're seeing. The next chart, let me show the Etheros results, and that'll probably get at the question to some degree. So these cards have apparently been calibrated because the Etheros, between 2 different cards, we get very, very similar results. You see that there is a little error there, and that is certainly, some of that is probably due to the emulator itself. But you see, roughly a dB-ish. There is a calibration question across different paths, and right now we're at about, I think, 2.5, maybe 2 dB of maximum error between cards. So I can talk more about the calibration offline. That's certainly, calibration is a pain in the neck. All right, so in summary, the high-level result is that the RSSI is not ideal. It's okay depending if you know what your cards are doing, but if you're going to use RSSI for localization, you really need to know what your cards are telling you. You can't just blindly assume that what it's telling you is completely accurate. And the emulator allowed us to characterize these cards in a fine-grained fashion. And if we were to do a localization experiment in the emulator, these natural effects and the variation that is present in these cards would be reflected in our experiments that we conducted in the emulator. All right, so now I'd like to bump up to some
variation in the environment, which really, it seems like that's the dominant factor.
For that particular case, yes. But it would be nice to, yeah. So let me move on to some link level tests that I've conducted. And I'm going to talk about 2 categories of tests, some off-channel behavior and some capture behavior. The first test I'd like to talk about is off-channel interference. 802.11b has 3 so-called non-overlapping channels. These are channels that are specified in the standard to not interfere with each other. But this isn't enough. So if we consider an idealized 2-dimensional topology where we have cells that look like hexagons, say, and let's imagine that each cell only interferes with immediately adjacent cells. Well, then using 3 non-overlapping channels in this 2D idealized environment, we can in fact assign channels in such a manner that no 2 adjacent cells are on the same channel. So that's good. That's what we want. But as soon as we bump up to 3D, this falls apart. So in the 3D case, we can't place all the cells, we can't assign all the channels in such a fashion that no two cells that are adjacent are on the same channel. Somebody's got to interfere. And then once we consider a real world, of course, it's worse. So many people have proposed using 4 channels, saying, let's cheat a little bit and squeeze more channels into the spectrum than the standard says we should be doing. And so the question is, how much interference do we get from people that are on a different channel? So the emulator let us analyze this in a very fine-grained fashion. So what we did is we used the emulator to construct the topology shown there on the right, where we have a transmitter sending to a receiver, and these guys are both on the same channel, in this case channel 6. And then we have an interferer which constantly blasts traffic on a different channel or the same channel. We varied it between channels 1 and 6. And so the question is, as we change that channel to interfere, and as we change the signal strength from the transmitter to the receiver, how much interference do we see? Or do we get any? And we measure this for different modulation rates. And so our results are shown in this chart here. The x-axis is the signal strength at the receiver from the transmitter that we want to hear. The y-axis is the number of packets out of 200 that made it from the transmitter to the receiver. So if all 200 make it, we say there's no interference. If all 200 make it okay, so the interferer, I should say, is always in this case at negative 82 dBm. So what we see then is if we're on the same channel, which is shown by the brown line here, what happens is as the signal strength from the transmitter to the receiver becomes less than that of the interferer, throughput drops drastically, as we'd expect. So that shows we're getting on the same channel, we get lots of interference. That's what we expect. As we move off channel, then, as the interferer moves off of our channel, the next 2 lines over, the purple and the green line, we see that the amount of interference is reduced, again, as we'd expect. The important observation is that once we're down to channel 3, so we're greater than or equal to 3 channels away, the performance is identical. So for this range of signal strengths that we looked at here, it looks very attractive to squeeze in more, to squeeze the channel spacing tighter than the standard specifies. So it looks very good. There has been some recent work that has advocated a different use of off-channel effects, and that is to use off-channel communication. So normally the standard expects that the transmitter and the receiver are on the same channel. But these researchers observed that if they're not on the same channel, sometimes they can still hear each other. So one motivation for this that they gave was to, let's say you have 2 mesh networks that are co-located, and you want to send data from one mesh network into the other mesh network. And you can't do this because they're on different channels. But if we put somebody in the middle on channel 3, maybe we could route the packet in such a manner that it is sort of translated between these 2 networks. So this was I think it's a pretty cool idea, but this paper didn't have a great evaluation. They went out into the hall essentially and said, yeah, it looks like it works. So again, the emulator gives us the power to analyze this in a very fine-grained fashion. So we, in this test, had a single transmitter, single receiver, no interfere in this case. And what we did is we sent, again, sets of 200 packets from the transmitter to the receiver and then varied what channel the receiver was on. And we repeated this for different modulation rates. And the 1 megabit per second result is shown here. Again, the x-axis shows the received signal strength from the transmitter to the receiver. The y-axis shows the number of packets that made it through. And the brown bar shows the on-channel reception. So that result shows, yeah, we have a very sensitive receiver, receives packets down to around negative 100 dBm. Now, as we move off channel, the receiver moves off of our channel, we get kind of what these authors expected. We get a degradation in throughput, which is what they expected. So our isolation between these 2 channels essentially grows. But communication is, in fact, still possible, like these authors expected. But once we move to 2 megabits per second, we notice things don't look so good. The on-channel reception, of course, is good, but as soon as we move even 1 channel over, we get very degraded signal reception. And in fact, if I were to show the 5.5 and 11, for the range of signal strengths I looked at, the only packets I received were at the on-channel case. So the takeaway here is that again, the off-channel interference things look good for cramming in more channels. The off-channel reception looked questionable. Certainly, if one were going to try and leverage this in a protocol, one would have to take into account the fact that it's not working so well for anything other than 1 megabits per second. And the higher level result that is here, that the emulator allowed us to characterize this sort of behavior in a very fine-grained fashion, and allowed us to gain insight that would be difficult to gain otherwise. All right, so the next couple tests I'd like to talk about have to do with capture. That is a packet, if you have two packets being received, do you get either one of them, or do you get a collision? What happens? The first test I conducted was to analyze capture as a function of interference delay. And so simplistic network analysis says, hey, if two packets overlap in time at all, they're both going to collide. A more accurate analysis says that what's going to happen is either we're going to lose, what can happen is we receive one in spite of the interference of the other, because when the two overlap, we get a degraded signal to interference and noise ratio, which may cause collision, may cause, but you can also get reception depending on the exact modulation. And in actuality, the exact places where these packets overlap matters. In particular, the front part of the packet is probably a little more fragile, and so this is what we want to investigate with this test. So what we did is we again had the topology of a transmitter, a receiver, and an interferer. And the transmitter and the interferer in all these tests, we made sure they didn't hear each other. And what we did is it's similar to that earlier interference test, except that the interferer in this case can only be heard at the receiver if the transmitter is sending. So if we imagine the packet reception is shown there on the right, where the red being a packet from the desired transmitter and the yellow or the gold being interference, what we caused was that the interferer can only be heard at the receiver after the transmitter's packet has started and after a certain delay has elapsed. And so we varied the amount of this delay and measured what happened to packet reception. And these two charts show the results for the top on 1 megabits per second, the bottom 5.5. The x-axis in this case is the amount of delay that we forced packets to undergo. The y-axis is the signal strength from the transmitter to the receiver. So on the top of each chart, the transmitter is very, very strong, and we're getting all the packets. And the bottom of the chart is when the interferer is much stronger than the transmitter and nothing gets through. So the z-axis is the number of packets received, shown by color. The dark blue in this case is if everything makes it through. It's not in the legend. I guess that's a feature in Excel that all the packets make it through. And on the interferer in this case is at negative 82 dBm, which is shown as a dotted line on the chart. So again, what we expect is as the interferer is weaker, we don't get as much. So the questions about the setup before I show features on it?
How do you control this delay? Is it in the host that's generating packets or in the emulator?
This is in, we altered the code on the FPGA to sort of, we left the channel off. So I should say what we controlled was when the channel was allowed to be on. So we were constantly blacklisting packets, so sometimes there might not be interference precisely at that time.
How long is the inter-packet delay?
It's very small. We were sending 1 megabit per second, 1,500 byte packets, so the dominant time was when there was traffic. It's a very small chance.
Okay, so it could be that you suddenly start seeing interference starting in the middle of the packet.
Could. But in general, it would be at the time that I'm showing you on the x-axis. So the way we did that was in the FPGA, we just detected the signal. When we detected the signal from the one, then we turned on the other one. And after a certain delay, we use the FPGA to count. Okay, so there's just a couple points I'd like to make here, and that is, first of all, that if there is precise synchronization, that if the interference is allowed to occur at the start of the packet, that's when behavior is the worst, because the receiver doesn't even have a chance to start acquiring that desired transmission at all. And then for the 1 megabits per second case, after about 32 microseconds, we see an additional benefit where it's able to, in this case, it's locked on to the signal, and it can, in fact, receive packets that are weaker than the interfering signal. This is because of the robust nature of the modulation.
How long is the preamble? Is that the preamble that you're...
This isn't the preamble. The preamble is around, it's maybe 100 and something microseconds. So it's well over 100, like 150 microseconds, something like that. All right, so just the results here was that, again, the traditional network analysis says if there's any overlap, that's bad. So what we want to do is we want to either synchronize or not synchronize. So this is generally what protocols do. What this test showed is that if we do precise down to the microsecond synchronization, that can actually be bad, and a little bit of slop hurts. So what we haven't looked at is how much precise synchronization there actually is in real devices, but if there is precise synchronization, that's a bad idea. So your protocol would be better probably making normative some sort of slot between packets. Just if you give it just a couple of microseconds, it's not going to hurt your overall throughput, and it can increase capture behavior. And again, it was the emulator that allowed us to gain this sort of insight.
It's not clear to me that the protocol can really do much here, right? Because the small delay that you're talking about can simply be due to propagation delays.
That's nanoseconds. We're up at microseconds.
The left hand of it, well, I guess you're still in microsecond range.
Yeah. So there is a question, there's maybe an open question which I haven't got at, which is exactly where does this kick in? You know, how many nanoseconds does it take to do that? That's a good question.
So I guess, I mean, we can take this offline if this has a complicated answer, but it seems like my guess might be that if you have two preambles fighting with each other, since that's specifically what the receiver is trying to lock onto, that might cause more adverse capture effects than a preamble, which is going concurrently with the middle of the packet. But from your description of your test, it sounds like you're overlaying the preamble of one with the middle of another packet, since you're not precisely controlling when that interference packet starts.
That would be, so the way I would like to conduct this, the way I would ideally like to conduct this is we can actually use the emulator to record packets. So I'd like to record a preamble, and then I can slam them, then I can precisely control when they slam into each other, and that would be a better test to run. Okay. So I'm not going to show this next result just in the interest of time, but basically I measured packet capture where I said we wanted both signals. So in this case we have two transmitters and a receiver, and we potentially want packets from both of these guys. What does the signal margin, how much stronger does one of these guys need to be than the other in order to successfully receive his packets? And we were able to characterize this, again, using an emulator. And what I will get at, what we use this data, I can get that as a result. I'll get back to that if people are interested. What we did is use this capture data then to drive an offline analysis. So these next results I'm going to show didn't use the emulator, but rather used data generated by the emulator to just generate some back-of-the-envelope analysis for how often we have problems such as a hidden terminal on the uplink. So if we consider a wireless LAN uplink, what we can have hidden terminals where we have a node talking to its access point and another guy that could possibly interfere with us. We could also have, in this case, they're both on the same access point, say. And we could have interference where B is talking to a different access point, but A's access point can still hear him. And in this case, I make a distinction between these two because A, in this case, it doesn't care whether A's access point doesn't even want to hear B. So clobbering it is OK. So this is slightly different than the hidden case where A's access point is interested in hearing traffic with both these guys. And there's a third potential problem we could have on a wireless LAN uplink of exposed nodes, where A and B take turns with respect to each other, thinking that they might interfere, but in reality, they don't. So we did some back-of-the-envelope calculations to see in a dense wireless network, such as we have in maybe this building, how often do these things occur? And characterization of capture is key in many instances. So what we did is in software, we gathered a radio map of a building in CMU's business school, and then in software we placed a number of nodes through this building, and then we associated them with the closest access point. The access point positions and the signal strengths were all real. And the signal strength between the nodes then we just modeled. And so we wanted to determine what happens. Are there lots of hidden nodes? Are there lots of nodes that might collide with each other? So again, we didn't actually perform packet level simulation. We just looked at the signal strength between the nodes and said, yeah, these two nodes could be hidden, these two nodes could be exposed. And the high-level result, which I'll be happy to talk about details more offline, was first of all, does capture eliminate hidden node collisions, hidden terminal collisions? And at 1 megabits per second, our results say yes. If everybody in the network were to talk 1 megabits per second, hidden terminal capture would trump hidden terminal. And more likely, people are talking at the higher modulation rates in a dense network. And at the higher modulation rates, hidden terminal effects can actually cause collisions. Capture does not always occur. However, in this network, what we found is that hidden nodes are rare, because if you are associating with the same access point, there's a good chance that you're quite close to each other and you can actually hear each other's signal. So then the next problem that could occur is interference. So somebody could be on the same channel as you but attached to a different access point. What we found is that there were lots of nodes for which that could be a problem, but that the capture results we obtained nearly completely eliminated that problem. If somebody was attached to a different access point, they were likely to be far enough away that their signal was weak enough that the capture effect of all the, even 11 megabits per second worked well enough to mitigate that external type of interference. And the last one that we looked at was exposed nodes. And we found that there were, in fact, for the cards using the default settings, there were lots of nodes that were taking turns with each other unnecessarily. So it looked from this back-of-the-envelope analysis that if the nodes, that there's potential for a great deal more concurrency in the network. We could be much more aggressive with, say, the carrier sense threshold to allow much more concurrency. And in this case, the emulator gave us the power to get the capture data to drive this analysis. All right, so now just to wrap up here, there's a related work to what I've been talking about today. Of course, test beds are all related to this, and they complement this work as I discussed earlier. The closest technique to what I've been doing is that of channel emulators, which are used by the telecom community. They use the same fundamental technique. They digitize a wireless signal and send it between devices. They have a different target, which leads them to a different design. They are interested in a very fine-grained modeling of a very small number of channels, usually one channel or more, or one or a small number between say a base station and a cellular handset. And the top-of-the-line channel emulator that I'm aware of is shown there on the right, Proxim C8. It supports a grand total of 8 independent channels, which isn't very many. The maximum network you could do with this channel emulator would be just 3 nodes. And you'd also need some you need some external componentry in addition to do this, because it really just gives you the channel, and it doesn't support, say, a half-duplex node. And the network emulator that I've developed, in contrast, allows up to 232 independent channels. And we directly support commodity wireless LAN devices. So some additional research I've done while I've been at Carnegie Mellon and wireless, I'm kind of ongoing work is I'm looking at the causes of asymmetric links. These aren't due to asymmetric channels. There's no such thing as an asymmetric channel. But link asymmetry can be caused by different power levels, etc. I've been looking at what the causes are of that, and I'd love to talk about that offline. I've also done some work on what we call chaotic networks. That is, everybody's going into the store, going into Fry's, buying an access point, plopping it in their home. How much interference is there between, potentially is there between these devices? And the quick result was there looks like in metro areas there could be a lot of interference. We haven't laid on top of this an analysis of capture, which might say, oh, there's interference, but capture eliminates it. Then I've also worked some with the RoofNet group at MIT. They had a great wireless test bed effectively, but they didn't have any way to control the analysis of that test bed. And so I worked with them to conduct some controlled experiments using the emulator to understand what they were seeing in the wild. And I've also looked at capturing, like I talked about earlier, capturing a channel with commodity cards and then replaying it in the emulator. And I also looked at the problem much earlier of 802.11 load balancing, which actually sent me down this path of emulation because I didn't have a good way to evaluate my proposed load balancing improvements. And some earlier work I did at CMU was related to pervasive computing. I developed a contextual information service. This let applications ask high-level questions using a SQL-like query about their environment around them. And on the flip side, it let the information providers provide simple information without processing a complicated SQL-like query. And some future research directions, naturally leveraging this emulation infrastructure. Most of the results I showed you were low level. I'm interested in popping up to higher level, running higher level experiments with this emulator. One natural choice from some of the results I've gathered, a more intelligent Mac, something that is aware of capture, would be, I think, an important contribution. I'm also interested in localization. There's been a lot of work on localization, and 95% of it or so in the CS community has been signal strength based, because that's easiest to get at. But I think that is fundamentally a limited way to do things. It's useful, but limited. And if you look at what the cellular providers have all gone to, they've all gone to some time of flight based localization. So I believe that's the direction, that's the future direction that wireless LAN devices will provide as well. Some sort of time of flight, such as time difference of arrival based localization. And once we have that technology, I think there are plenty of exciting things we can do about security, trying to deny people access to a network based on their location. And of course, they'll try and spoof their location. I think there are lots of proof of location types of protocols that could be looked at as well. And then one other approach is there's been some work at CMU previously saying if I'm multi-homed on the internet, if I have multiple ISPs, I can get improved network performance. Well, if you have a network where my neighbors and I all have wireless devices, we can potentially share each other's connections. So if I have provider A, I could potentially leverage provider B, provider C, ignoring the lawyers for a moment. But I could potentially leverage those other taps into the internet to get better performance. And in conclusion, wireless networks are, of course, going to be very important in the future, and the lack of realistic experimental tools has, I believe, hampered the wireless research community. And I have developed a physical layer emulator that provides much of the control of simulation with much of the realism that one obtains in a test bed. And this can provide insight that is difficult to gain with either of the other techniques. And it can be the basis for developing future wireless improvements. Thank you.